Hello and welcome back. So what I want to talk to you about today is noise. And noise can get into your circuit from all sorts of sources. So you can have a noisy supply, you can have immunity problems, so from radiated sources, or your layout can be poorly done. Now, for these sort of problems, usually you have solutions. Either use some proper supply filtration, use some shielding around your circuit, or actually hire a layout engineer, so not some freshman. But I want to talk to you about a different kind of noise source. What I want to talk to you about is noise that is coming from the actual components that you're using. So noise that is generated inside the circuit, noise that is not coming from some external source. So let me give you an example of what I'm on about. So I built this little circuit right here with an op amp, and I'm supplying it from 25 volts. And basically this circuit is a dual op amp amplifier. So the total gain of this circuit is around 2000, but the input is connected to ground. So just like we see here, 0 volts. Now if we run this thing and look at the output, we see around 6 volts. So this is coming from the offsets inside the op amps. But the important thing to notice here is that the output voltage is a very straight fixed value. Now, what do you think this circuit will behave like in real life? Will it be the same or will it look slightly different? Let's just see. So here I got my circuit. I got my probe with a low noise connection, so very short lines. If I look at the ground only, we can see the noise of the ground and of the oscilloscope. So anything that's above this is actually generated by the circuit. And if we measure the output of the circuit now, we see that there's quite a lot going on. So it's way more than we got with the initial measurement, so when we were measuring just the noise floor. So what's going on? Well, if you're curious about where all this noise is coming from, how you can simulate it using LTspice, and of course what you can do about it, then keep watching. So to start things off, the first thing we need to talk about is how we actually need to set up the simulation to perform a noise simulation. So in our previous simulation, I used a transient simulation. But we don't need to do that, we need to perform a noise simulation. Now there are a few input fields here. So first of all, what is the output and the input signal? Mainly the output signal is important, the input signal is there for some other reasons, but you still need to fill it out. What type of sweep you are making? So this is just like an AC sweep, so you can have decade or octave or whatever, how many points per unit of frequency, and then a start and stop frequency. So let's see this little circuit here. So what I got here is a simulation in which I have an input signal source, couple resistors, and an output net. Now if I simulate this, and we look at the output, so we can see the output noise density. So this simulation will not directly tell us how many volts peak to peak of noise we are getting, but rather what is the density of noise in the output spectrum. So what is this helpful for? Well, we can find out what will be the peak-to-peak noise by going over the output noise, and by pressing Ctrl and clicking on the name, we get this little window appearing, which basically will tell us what is the RMS noise for our given frequency. So basically, this performs the integral of our displayed function. Now from here to peak, we simply need to multiply it by 6 or 8, depending on what literature you're looking at, but roughly that will be your peak-to-peak noise. Now it's important to mention that in this simulation all the noise is coming from the resistors. So the resistors have thermal noise, and this is being represented here. Now the simulation is not taking into account any of the other resistors in the simulation. So our output noise is created from the contribution of these two resistors that are placed in the circuit. Any other component which we have in the simulation is completely ignored. So if the components in your simulation are not connected to the designated output, then the simulation will ignore them. Let's look at a more complex example. So what I got here is a circuit that has a transistor amplifier, so the basic transistor amplifier. And if we run this, again in the same 1 Hz, 10 MHz range, and we look at the output, we see that it's no longer a straight line. So what I want to show you with this simulation is that LTspice doesn't just simulate thermal noise coming from resistors, it also simulates shot noise and flicker noise associated with semiconductors. And now if we look at the noise from our resistor, we see that it's no longer flat. So the resistor has uniform noise density output. But the simulator is not showing us the absolute noise generated by the resistor, it's showing us how the resistor is contributing to the output noise. So the resistor on its own would have a flat noise output. But being passed through this amplifier, only this region of the noise that the resistor is creating is getting to the output. Now, one interesting thing we can do right now is see which of the components has the biggest contribution to the output noise. So we can simply go through all of the components, and we see that the transistor has the biggest amount of contribution to the output. So right now the output noise is around 8.1 microvolts RMS. Now if I simply change the transistor with random one, let's say this one, and re-simulate, we get 3.9 microvolts. So changing the transistor has a significant influence on the output noise. Now this of course has to do with how well the transistor is modeled, but you can get a very good idea about how your components are influencing the output noise. Now speaking about noise contribution, let's take this example. So what I got here is an op-amp circuit in which I'm amplifying an input signal. And I want to amplify it by a factor of 3, but I want to know which of these resistor values will give me the least amount of noise. Now to do that, I can simply run a dot step simulation and see that I have a ton of measurements, and if I try to measure the RMS, well, we can't integrate it since there's multiple runs, so this works only with a single run. Now you can do something very nice in this case, and that is use a .mesh statement, so a measurement statement, in which we're integrating the noise using this sort of statement. And this way, if we now go to the error log, we can see that out of the 5 steps, so first step the resistor was 100 ohms, in the last step it was 1 mega ohm, the highest amount of noise was the simulation in which we had the highest resistor, and the lowest amount was the one in which we had the smallest resistor. So if you want to go through various parameters, an easy way to find out how your output is responding, so which out of the simulations is the best one, can be done with this sort of measurement statements. Now the interesting thing about the noise simulations is that they're not just noise simulations. They're also operating point simulations, and they're also AC simulations. So what I mean by this is that if I now go on my circuit with my mouse over a random net, let's say the output net, if I look in my bottom left corner, I can see that the output voltage is 8.87. So the first thing the simulation did was calculate the operating point. This is helpful to see if the circuit is actually working. So you can either first perform an operating point simulation or a transient simulation to see that the circuit is working, and then perform the noise simulation. Because otherwise, so let's say I'm trying to amplify by 10 volts. So that would give me 30 volts. But my output noise now is completely different because the circuit is no longer working. So right now the output is stuck at 15.9 volts because that's the maximum voltage the op-amp can output. It can't get anywhere near the 30 volts I'm trying to ask of it. So the noise measurement isn't working well either. Now to show how this is also an AC simulation, we can add some more traces. So when we do this add traces to plot, we get all of the traces that exist in the simulation. So we get our output noise, input noise, voltages through the resistors, and we get this gain plot. Basically, this is telling us how the circuit is amplifying. So something is not going very well. Let's simply add some single resistor values. And now we can clearly see the gain of the circuit. So we're getting a big bit of gain peaking here at 1 MHz for some reason. And with increasing resistor values, this is getting worse and worse. So that's why in this noise simulation we're getting these huge spikes. Now, another interesting trace to look at in these simulations is the input noise trace. Basically, the simulation will tell us the output noise of the circuit, but it will also tell us the input noise. Basically, it's the output noise divided by the gain. Basically, what the simulation is telling us is what the minimum input signal needs to be to actually be registered, because anything below this noise floor cannot be measured, because the circuit on its own already has this amount of noise. So in this case, this input noise comes from the op-amp itself and the resistors. So it's not the input noise of a certain component, but it's the input noise of the entire circuit. Now, speaking of the noise coming from the various components, how do we know if the op-amp is modeled correctly? Well, we know that the resistor on its own will have noise, and LTspice models this. The question comes with semiconductor components or models that are attributed to certain components. Now, a nice trick that we can do is tell the simulation to not take into account the noise of certain components. This works well with resistors. So if we take this circuit, we can simply type into the value of the resistor that it's a noiseless type. So basically it's an ideal resistor. And what this does, it eliminates the noise that that resistor was generating in the circuit. So now, if we look at the output noise, we can no longer click on the resistors to see their contribution. So all of this output noise is coming from the op-amp itself. And this is a nice way to check if the op-amp is actually working. Likewise, now if we look at the input noise, we see the input noise attributed to this type of op-amp. So the simulation is telling us that this OP27 has around 3 nanovolts of root hertz noise, ranging from 100 Hz to around 1 MHz. And if we check this with the datasheet, we see the exact same value. So what I got here is the noise density output of the OP27 in the datasheet from analog. So they did a good job at modeling this component. And this is a good thing to check when working with other components, especially if you have to import the model. So if you're not using models that are built in. Now all this looks nice. Let's see how we can apply all these things and features to an actual circuit. So what I got here is a circuit we started off with. This is my dual op-amp amplifier that has its input connected to ground. So first of all, we need to change the type of simulation, so no longer transient simulation. We're interested in a noise simulation. And if we run this thing, we see that it has quite a lot of output noise. And if we integrate it, we get around 11 millivolts of RMS noise. Now, if we multiply this by 8, we get almost 90 millivolts of peak-to-peak noise. So the noise that the circuit is predicting is very close to the noise that we actually measured with our initial circuit. So now that we know that the circuit is noisy, we know that we're modeling it correctly, what can we do about it? Well, one of the things we can do is understand how this noise is being generated. So we can look at the various components and try to see which of them has the most contribution. And we see that the biggest contribution, so other than the op-amps, is coming from this R1 resistor. So we can simply reduce the noise it generates by reducing its value, but keeping the gain factor. So we're going from a 10.96 millivolt RMS noise, and if we, let's say, divide these two resistors by 100, so we keep the gain factor but just reduce the resistor values, and we resimulate, we now have a total output noise of 9.9. So it wasn't a huge reduction, but we did reduce some of the noise. And now we can see that all of the resistors have almost negligible contribution. So the rest is up to the op amp. And well, there's not much we can do about that unless we completely change the op amp. So with a lower noise one. So how noisy is this op amp anyway? Well, another way we can check that is to just simulate the op amp itself, so without any other circuitry. So basically what I did here, I took an op amp, connected it as a unity gain amplifier, and I just need to edit this noise measurement statement to see exactly what the op amp is contributing noise-wise. And if we do this, we see that the op amp has quite a lot of noise, so just on its own it's generating almost 60 microvolts. And since it's in the unity gain configuration, this is almost exactly the same as its input noise. So this is not a low noise op amp. Best thing to do would be to simply choose a good op amp. But what else can we do? Well, if we look at the output noise, we know that the simulator is plotting out the noise density. And the RMS value, and therefore the peak to peak, is this graph integrated. So one more thing we can do, since we can't really do anything about the op amp, is reduce the area of the graph. So the area that's being integrated. Or in other words, reduce the bandwidth of the amplifier we've just created. So right now the amplifier has a gain of around 2100 up until a few kilohertz. Now if we would reduce this bandwidth, theoretically we should get a lower noise. So let's try that out. So I added this 100 nanofarad capacitor on the feedback resistor of the first op amp, and now the bandwidth has been substantially reduced to below 100 Hz, but also the output noise density. And now if we look at the RMS value, we went from close to 10 millivolts to close to 1 millivolt. So the quantity of noise that your circuit is generating is also dependent on its bandwidth. So in general, if you want to reduce your output noise, you need to choose smaller resistor values. That way you will reduce the thermal noise they're contributing. You can reduce the bandwidth of your amplifier, but that's not always acceptable. Or you can use low noise parts. And in this case, the LM2902 is not a low noise part. So let's just see if this bandwidth reduction thing actually works in practice. And we can do that with the circuit we started with. So if we recheck again its output noise, we see the 100 something millivolt of peak to peak noise. But if we look at the waveform a bit more closely, we can also see that there's a lot of high frequency content in this. So we see a lot of very thin, very sharp spikes going through this waveform. Now, if we take the capacitor and add it into the circuit, so I prepared this little connector here to ease this connection, we see that our waveform now looks completely different. So we didn't just reduce our peak to peak noise, but we also changed the shape of the waveform. So we see that we no longer have a high frequency content, so there's no more spikes going through it. We just see this slowly changing waveform. So the spectral content has definitely been reduced. Now a better way of seeing this would be using a spectrum analyzer, or if the FFT function on your oscilloscope works very well, then you can see this change also with that. But just by looking at the waveform, it's pretty obvious that changing the bandwidth has completely changed how the noise the circuit is generating looks like. Now as long as the noise that you're measuring has tens or hundreds of millivolts of amplitude, this way of measuring is completely fine. But most of the circuits we simulated today had noise in the order of tens or hundreds of microvolts. Now that is way below the noise floor of a cheap oscilloscope. And sometimes it's also below the noise floor of an expensive oscilloscope. Now, if only there was a way in which you could measure very small voltages without having to spend a fortune on test equipment. So all in all, Hope you got some useful information about this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.